So now that we have a design that can do memory operations and also can do adds, of course it can do all kinds of arithmetic and logic unit instructions. So all the shifts, all the ANDs, ORs, binary operations, subtraction, addition, they are all done in the same way as the add. So we have all those operations. We have loads and stores. What we need next is to be able to make decisions. To make decisions, we'll need to be able to process a branch. So for the branch operation, what we're going to need to do is to look into having another adder in our design, because we need to be able to compute a new value for the program counter. So in the case of a branch instruction, this is the format. Just recalling the format of a branch instruction, it has two registers, and it has an opcode and has function codes, 3 bits for the function codes. And remember that the function code actually differentiates the type of branch that I'm executing. Let's consider the execution of branch not equal. The other ones will be similar later. So for the branch, I'm going to have to do something similar that I did for the other instructions. So I'll take the bits 15 to 19 from the instruction binary code, and I will specify that as the first register for my arithmetic and logic unit. And then I'll take the bits 20 to 24, and I will specify as the second entry to my arithmetic and logic unit. So I take in the registers RS1 and RS2 and send it to my arithmetic and logic unit. And because this is a branch not equal instruction, I'm going to then tell the instruction, tell the arithmetic and logic unit to perform a subtraction. And I'll take the 0 output of my arithmetic and logic unit to control the control logic for the control logic of the branch operation. So based on that result, I'll make a decision. And remember that what the branch instruction may do is to take the value of the immediate, sign extend to 32 bits, shift left by 1, because remember there is an implicit 0 in the branch instructions. So after I do my sign extension, I need to shift left by 1, and then I will provide that as one of the inputs to my adder. The other input to my adder is the program counter. So now, with the program counter and the value of the immediate sign extend 32 bit, I can compute the value of my branch target. My branch target will then be the new value of the PC if the branch condition was true. And I can tell in register write, I'm going to tell the register file that it should not write, because this is a branch instruction. So looking at the whole design now, what I did from the previous slide, I took this design down here that we already have for the add and the load store. And I have, in addition, this adder here, that's the adder for the branch, and I have one more adder now. That's the adder that will add 4 to the program counter. So I need to compute 2 possible values to the program counter. One where I add 4 to the program counter, the other where I add the value of the immediate sign extended to 32 bits and shifted by 1, which is the target of the branch. And now what I need to do, I need to make a decision which one of those 2 values of the program counter should be written back into the program counter. Because I have 2 possible values that go to one place, I again need one of those switches that's called a MUX. And so the 2 inputs to my MUX now will be PC plus 4 or the target of the branch. And based on the branch outcome, I'll select one of those to be the new value of the program counter. And the way I control this is with a signal called PC source that will tell this MUX whether the branch condition was true or not. And of course, I will obtain the logic for the PC source from, in the case of the branch not equal, from the 0 output of my arithmetic and logic unit. I have replaced my control to the arithmetic and logic unit here with an operator plus several bits that come from the instruction format, because remember I have the function codes that will determine what is the operation that I need to do in my arithmetic and logic unit. So this completes the single cycle data path for now, but we still need to look at the different steps that I take to execute each one of the instructions. So this will be an overview of the data path as I execute each one of those types of instructions. So let's first look at the four steps of an R-type instruction. So the first step is to fetch the instruction. So fetching means that I take the value of the program counter, I send to the memory, and I receive back the word that contains the binary representation of the instruction. Then I need to decode. Decode corresponds to taking the corresponding bits, bit fields from the instruction code and sending them to the register data file, and also at the same time looking at the value of the opcode so that I can compute the value of all those control signals that will tell me, tell the processor what it should do in each one of those muxes that I have in the architecture, and also what the arithmetic and logic unit should do for this instruction. And then the third step is for the arithmetic and logic unit to execute the instruction, which means to do the calculation that the instruction needs it to do. And it will gonna use parts of the opcode to generate the arithmetic and logic unit function. For example, we're gonna look at the function code to decide whether it's an add, whether it's a sub, or whether it's an and or an or, etc. And finally, the last step of this type of instruction, that R-type instruction, is to write the value of the register that was computed, write the result into the register file. So there are 4 steps to the execution of an arithmetic and logic unit instruction that is an R-type instruction. Fetching instruction, decoding, that is finding out what the instruction is supposed to do and retrieving the value of the registers from the register file. Execution, which happens in the arithmetic and logic unit and does the operation that the instruction specified, and write back, where I take the result produced by the arithmetic and logic unit and I write back into the register file. If I look in my design, the design will highlight the lines that are used for each one of the steps. Fetching the instructions use these lines here, send the program counter to the instruction memory, increments the program counter, and if it's not a branch instruction, this will simply select PC plus 4 to go to the new PC. Then the decode will be the process of sending the corresponding signals to the arithmetic and logic unit control unit and retrieving the correct registers from the register file. And then I have execute. Execute is the operation that happens in the arithmetic and logic unit. And then I have write back. Write back is the process of taking the result of the arithmetic and logic unit and sending back to this path to the registers. Now, how about a load instructions? What are the 5 steps for a load instruction? The first step is fetch. The second step is decode. Those steps are always the same for all the instructions, because I needed to get the instruction from the memory and I need to find out what the instruction is supposed to do. So, but in the decode, in the case of the load, it's only reading one register from the register file, because the other operand comes from the sign extension of the immediate value. And then the arithmetic and logic unit in this case will be computing the address in which I'm going to do the access. So it's going to be adding the value of the registers to the value of the immediate. And then, so that's the execution. And then I'll now use the result from the arithmetic and logic unit to access the memory. So my 4th stage in the load instruction is the memory stage. And then I have a 5th stage in the load instruction, that is the write back stage, where I write the data that I obtain from the memory into the destination register that's specified by those bits. So the data path for the load instruction will follow this these paths here, and we'll use all those lines that are bolded in this. So important to note here is that, this line should be bold too, is to note that the arithmetic and logic unit is adding the value of the source register to the extended sign extended immediate, obtaining the address, telling the memory to read, getting the value back, and writing into the register file. For a branch or unequal instruction, I have again a fetch, I have a decode, and then the arithmetic and logic unit will subtract the value of the two registers to find out whether the difference is 0 or not. And at the same time, there will be that additional adder that we have to design that will be adding the 12 bits of the instruction immediate fields, shift left by 1 and sign extended, to compute the branch target address. And then the 0 status of the arithmetic and logic unit will be used to add the value to the PC. So the write back stage of the branch unequal is not writing back into the register file, it's writing back into the PC, because this is a control flow instruction. So the data path for the branch is different than the data path for the other instructions because I don't have a write back to the register file. What I have is a write back to the program counter. So if I add the control units to this design, this is my control unit, and now it shows how the control signals for all the different MUXs is computed based on the opcode of the instruction. So I look at the opcode, that's the bits 0 to 7 of the instruction, and based on the opcode, I know what to send as a control signal to each one of these units. And again, I send some of the bits to the arithmetic and control unit. So the control is divided between this main control unit and the arithmetic logic unit control. We are almost done, but we haven't done the jump and link instruction yet. For the jump and link instruction, what I have is, this is the format for the jump and link instruction. The immediate is specified in this format from the bits 12 to 31. And I have the an RD registers in the bits 7 to 11. So the jump and link instruction will save the value of PC plus 4 in the specified register. That's the return address. And but note that the instruction is general. I could use any register as the destination, and that's how I do a common jump, by using the register, specifying the register 0 here, which will take no effect. But I could use any one of the other 31 registers of the machine in here. The practice is that we usually use just RA is the register that we specify here, but we could specify any one of them. So and what we'll do now is to change the value of the program counter. So I need to change the value of the program counter to be PC plus the offset. And the target of the branch will be within plus or minus 2 to the 19 locations, because I have 19 bits that I can specify here. And it has to be 2 bytes apart. So the consequence is that I can jump plus or minus 2 to the 18 32-bit instructions. The immediate encoding is optimized similarly to the branch instructions to reduce the hardware cost. So this, what looks like a fairly crazy encoding here for the immediate, with those bits shuffle in this way, it was done very carefully to make the hardware easier to design. So the data path for the jump instruction consists in, after I do the fetch, I specify to the register file a value to be, a register to be written to, because remember the jump and link will save the return address in there. And now I need to take the value of the PC plus 4 that I computed here, and this value is the value that I need to send to my register. So because I have a jump and link in this machine, I need one more input to my MUX now. This switch that before had 2 inputs. Now it has 3 because it has the value of PC plus 4, which are going to write back into the register that was specified in the instruction. The register was specified in the bits 7 to 11 of the instruction. The other thing that I'm going to do, I'll take my immediate, send to my immediate generator unit. I'm going to tell the immediate generator unit that this is a jump and link instruction so that this unit will know how to do the shuffle in order to obtain the proper immediate. I will shift left by 1 because this immediate also has a hidden 0. Remember, the implicit 0. And I will then add this to the PC because a jump and link is relative to the PC to obtain the destination. So now that I have the destination, I can decide with my MUX here whether I will be sending. So I also need to improve this PC control signal here, PC source signal, so that in the case of jump and link, I also send this to the PC. I send the new value of the PC to the PC, and I do that every time. It's not conditional in the case of the jump and link. So this is the end of our single cycle data path. With this design, we are able to execute in hardware all the arithmetic and logic unit instructions, load and store instructions, jump instructions, and branch instructions.